Okay, so can you hear me?
Yes, sir.
Yes.
Okay. So everyone is here, right? I think Shushmita is not able to join nowadays. So, okay. Okay, so let me start. Okay. So let me just recall a bit what we did last time about the Hopf-Reno theorem. We were talking about complete manifolds. So we defined a distance function on a Riemannian manifold. The distance between 2 points is the infimum of lengths of piecewise C1 curves joining the 2 points. And we showed that it is a metric which induces the same topology as of the manifold. And then the Hopf-Reno theorem is about the connection between the completeness of the metric. So whether the Riemannian manifold is a complete metric space versus the completeness of geodesics. That means whether geodesics are defined for all time, or in other words, if you look at the geodesic vector field on the tangent bundle, whether the geodesic vector field is a complete vector field. So that means its integral curves are defined for all time, right? So then we said that the manifold is geodesically complete. So the Hopf-Reno theorem says essentially that these two are equivalent. The Riemannian manifold is complete as a metric space, if and only if it is geodesically complete. Okay. And so in either case, we'll say that the manifold is a complete Riemannian manifold. So the first step in the Hopf-Reno theorem is to show that, so there are 5 conditions, A, B, C, D, E. So the first step is to show that A implies E, where A is the statement that for some point P, the exponential map based at P is defined on all of TPM. So this we want to show implies condition E, that any point Q in M can be joined by a length minimizing geodesic gamma from P to Q. Okay. So if the exponential map is defined on all of TPM, then what this is saying is that the exponential map is surjective. If it is defined everywhere, then it is necessarily surjective. All right. Not only is it surjective, but I mean, the image, in the image, I mean, the image contains a geodesic which is length minimizing for each point in the manifold. That means there is a shortest length curve for each point in the manifold from P to Q. So just one thing about the proof. So what we did is, the idea is to look at the distance function from a point. So what we were doing is we have the point Q and we want to go from P to Q. So what does that mean? That means we want to decrease the distance from P to Q, right? We want to keep moving in such a way such that the distance to Q keeps decreasing. And the natural thing to try and do is to make the distance decrease as fast as possible, right? So the first step was to take a small epsilon geodesic ball around P and then choose a point x naught on the geodesic sphere of radius epsilon, which is closest to Q. So that means the distance from x naught to Q is the infimum over point Z in the geodesic sphere of radius epsilon around P of the distance from Z to Q, right? So we're going as close to Q as we can amongst points which are at distance epsilon from P. Okay, and so then x naught is the image under the exponential of some epsilon v, where v is a unit tangent vector. So then we look at the unit speed geodesic gamma t equal to xp of tv, right, whose initial condition is v, initial velocity is v. And then the idea is to show that this geodesic gamma t will actually reach q, right? And so what you want to show is that along the geodesic gamma t, the distance to q, it decreases as fast as possible. So if I move a distance t, then the distance to q will decrease by t. Okay, note that this is the fastest possible decrease of the distance because the distance function is 1 Lipschitz, right? In each variable. That just follows from the triangle inequality, right? The distance function in any metric space is always 1 Lipschitz with respect to, if I fix q, then as a function of the first variable, it is 1 Lipschitz by the triangle inequality. And so, I mean, the distance from gamma naught, which is p, to gamma t is exactly t, is at most t, because gamma is unit speed. So if this equality occurs, that the distance gamma tq is distance pq minus t, this means that we've decreased the distance as much as possible, right? We've decreased it by t as much as possible. So then the idea is you look at the set of times t for which this holds in the interval 0 to d, where d is the distance from p to q. And then you show that the endpoint d belongs to this set A, and that will tell you that gamma of d is equal to q, and so you're done. All right. So first note that A is closed, and then what you want to show, so therefore A contains its supremum because it's closed. And so you want to show that the supremum of A is D. So what we actually showed is that if a point T naught belongs to A, then T naught plus delta for delta small enough also belongs to A, if T naught is less than D. All right. So that's what we showed. So to do that, we looked at the point gamma T naught, we call that X. Then we looked at a geodesic sphere of radius delta around X, which is disjoint from Q. And then, like we did in the first step, we chose a point on this geodesic sphere Z, which is closest to Q, okay, on this geodesic sphere. And then what we showed is that the distance from Z to Q has decreased by exactly delta as compared to the distance from X to Q. So we showed that the distance from Z to Q is D minus T naught plus delta, and D minus T naught is the distance from X to Q, right? So that means the distance from Z to Q is the distance from X to Q minus delta, right? So when you choose this, you can think of this as a discrete algorithm, a discrete time algorithm. You move in steps of size delta. Imagine you're walking in the manifold and you're moving, your step size is delta. So where do you want to move at each time? You want to move in the distance delta in the direction which decreases the distance to Q as much as possible. And then what we show is when you do that, the distance to Q decreases by exactly delta, right? So then what you do is you look at the geodesic alpha from X to Z. And then we showed that if I look at the curve gamma up to time T naught composed with alpha, then we showed that this is length minimizing from P up to Z. And therefore, by a previous result, it is a geodesic. Okay. And so the concatenation of these two geodesics is a geodesic. That means that alpha must be part of gamma, right? And so, so Z must be gamma of T naught plus delta, right? That's what we did. And so that then we were done essentially. Right? You remember this? Is this okay? Yeah. So we showed gamma restricted to 0 T naught dot alpha as a geodesic, and therefore Z is equal to gamma of T naught plus delta. And so therefore T naught plus delta belongs to the set A, and so we're done. So the only point I want to make, which I forgot to mention last time, is that in this proof, you need T naught to be positive. So T naught we were taking to be the supremum of A. So here you need T naught to be positive, because if T naught is 0, then gamma restricted to the interval 0, 0, that's just a singleton. So, I mean, that's just a constant. Singleton dot alpha is a geodesic, doesn't say anything about alpha and gamma, right? Is it clear? So here you need T naught to be positive, and the reason that T naught is positive is because the same way that we showed the distance from Z to Q is the distance xq minus delta, that same argument will tell us that when we do this first step, the distance from x naught to q is the distance from p to q minus epsilon. All right. And that will tell us that the point, the time epsilon belongs to the set A. Right. That will tell us that the distance from gamma epsilon to q is equal to distance pq minus epsilon. So epsilon belongs to the set A. Epsilon is positive. So T naught is greater than or equal to epsilon. Okay, so therefore T naught is positive. Is this clear?
Yes.
Yes, so this point I forgot to mention, that the supremum is positive. So the point is that the distance from x naught to q is the distance from p to q minus epsilon. Okay, so the distance decreases by exactly epsilon as much as possible. So what does this tell you? So in your calculus, you might have talked about gradient flows and gradient curves of a smooth function. So those are, even in school, I think you might have talked about them. Those are curves of steepest descent, right? Those are curves of steepest descent. And what we're using here is actually the fact that if I look at the distance function from Q, then at the points where it is differentiable, it may not be differentiable everywhere. At the points where it's differentiable, the gradient lines of the distance function from Q are the geodesics passing through Q. Yeah, and what we're doing is sort of a discrete gradient flow. We're doing a discrete gradient flow in this proof. Do you understand what I'm trying to say?
So can you repeat this thing?
Yes. So do you remember what is the gradient flow of a smooth function?
Yes.
Right. So you look at the gradient vector of the function, right?
Yes.
Let's say we're in Rn. Let's say we're in Rn. You look at the gradient vector of the function. So that defines a vector, right? And suppose I look at minus the gradient, all right? So
Steepest ascent and steepest descent.
exactly. So that will give me the gradient, the direction of the gradient vector field will give me the direction of steepest ascent, and minus the gradient vector field will give me the direction of steepest descent, right? So
Yes.
you can do the same thing in a Riemannian manifold. Oh wait, so so let me just okay, sorry. So gradient flow. So you have Mg is a Riemannian manifold, and F is a C infinity function on M. So if I take a point P and M, then GP, this is an inner product, so it's a non-degenerate bilinear form. So it induces an isomorphism between TPM and its dual, right? So let me call that GP hat from TPM to TPM star or T star PM, the cotangent space. What is the isomorphism? V goes to the linear functional, W goes to GP of VW. Right? This is the isomorphism. Yes?
Yes. Yes.
Now, if I look at DF at P, this is a linear map from TPM to R. So DF at P belongs to TP star M. So therefore, there exists a unique vector which I'll call grad F at P in TPM such that GP hat, this isomorphism, maps the gradient vector grad F to the derivative dF at P. Right? Yes?
Yes, sir. Yeah. Yes.
The inner product gives you a canonical isomorphism between the dual and the cotangent space and the tangent space. DF at P is an element of the cotangent space. So it corresponds to a unique element of the tangent space. That element we call the gradient vector of F at P. Okay. So what it satisfies is that DFP of V is equal to inner product grad F P V for all V in TPM, right? That's what it means to be related by the isomorphism GP hat. Is this
Yes.
clear?
Yes. Yes. So this
Right.
same thing we can do for pseudo-Riemannian manifold as well, right?
Correct, correct. As long as you have a non-degenerate bilinear form.
Mhm.
So we will do this also for symplectic manifolds, where you have an alternating non-degenerate bilinear form, and then the duality will give you what's called the Hamiltonian vector field. Instead of a gradient vector field, the derivative will give you what's called a Hamiltonian vector field. Correct. So we can do this as soon as you have a non-degenerate bilinear form on the tangent space. So note here, since we have an inner product which is positive definite, it satisfies Cauchy-Schwarz inequality. So this is something special to inner products. This you can't do with the general pseudo-Riemannian metric. Here what will happen is that mod of DFPV, suppose V is a unit vector, then this will be less than or equal to norm grad F at P and greater than or equal to minus norm grad F at P. Right? For all V unit vector, right?
Yes.
And equality, if and only if V is equal to norm grad FP for the first inequality, and or V is equal to minus norm grad FP. Okay, so this tells you that the gradient direction and minus the gradient direction, these are the directions in which the function increases the fastest and decreases the fastest. Is this clear?
Yes, sir.
Right. So now, if I look at the function f of p equal to the distance from P to Q. Okay. So then for P close to, so if I'm looking at, so this is Q and this is P. So if I take a geodesic ball around Q, then I know that first of all, F is 1 Lipschitz by the triangle inequality. So by passing to a limit, this implies that the norm of grad F is less than or equal to 1 everywhere, right? Is this clear?
Yes.
You just look at, f of p minus f of p prime, and you divide by the distance from p to p prime. You take mod of that, and you let p prime tend to p. Then what you'll get is that converges to the inner product of grad f with v, where v is the direction in which p prime converges to p. Okay, so so you can show this. This is not hard to show. Okay, so on the other hand, if I look at geodesics passing through Q, right, then along these geodesics, I know the distance from Q increases exactly like T, like the distance along the geodesics. So f of gamma T, this is exactly equal to T, right? If gamma is a geodesic XQ TV, mod V equal to 1, and T small. So inside a geodesic ball, right? So
Yes.
what does that tell me? That tells me that I'm increasing as fast as possible, right? Because this is 1 Lipschitz, and this curve is the distance from Q is at most T. So that tells me the gradient direction grad F of gamma T is equal to gamma prime T. Okay, or if I write this in the other way, then it will be easier to see that gamma prime T is equal to grad F of gamma T. Right? In other words, is this clear? Because in this direction, if this distance is T, and I move a little distance S here, then how much do I increase? I increase by T plus S, right? So in the limit, what I get is that the inner product of grad F with this tangent vector gamma prime, this is equal to 1. And I know it's less than or equal to 1. So therefore, I have equality in Cauchy-Schwarz. So that means that grad f has to equal gamma prime t. Is it clear? Okay. So I'm not doing the details. You can work this out. I'm trying to give you the idea. It's an easy exercise. You can work this out. Is this all right?
Yes, sir. Yes, this is fine.
Yeah. Okay. So what does that mean? That means geodesics through Q, sorry, are integral curves of grad f, and grad f is the, let me write this as d sub q. This is the distance function from the point q. Okay. All right. So now if you come back to the proof of the Hoff-Reno theorem, it should be more clear what we're trying to do. We're trying to go from P to Q. So we're looking at the distance function from Q to any point, and we're trying to make that decrease as fast as possible, right? So that's what we're doing. We're doing a sort of discrete gradient flow. You understand? We're moving a step epsilon at first in such a way that the distance to Q decreases as much as possible. We're minimizing over the points in the sphere of radius epsilon, the distance to Q. Do you understand? Okay.
Yes.
So we're doing a discrete gradient flow, right? The Hoff-Reno theorem, what we're doing is a discrete gradient flow, where the time is discrete. We're moving in step time. Instead of time being a continuous variable, we're moving in discrete steps of size epsilon, right?
Yes.
Okay, so that's the idea behind the Hoff-Reno theorem. Okay. Is it clear now what I meant by a discrete gradient flow? That's what we're doing basically. Okay. Any questions? Anyone? Any questions? Okay. So then let's finish the proof of the Hoff-Reno theorem. So we had, let me just switch to the better view. So, right. Okay. Yeah, so we had these 5 conditions, A, B, C, D, E. So we've shown that A implies E. Now we have to show that A, B, C, D are equivalent. So that's not hard to do actually. Once we've proved A implies E, the rest will follow quite straightforward. So let's do A implies B, that if the exponential map at P is defined on all of TPM, then the closed and bounded sets of M are compact. So bounded means with respect to the distance function. So that is simple because if I take B, which is a closed and bounded subset of M, then by, this is not F, this should be E. I know that every point in B is the image under the exponential at P of a vector whose length is bounded by the distance from P to the point in B, right? So the ball B, I mean this set B will be contained in the image under the exponential of a closed and bounded ball in the tangent space, B R0 closure, where R is the max supremum of the distance from P to Q over points Q in B. Is this clear? this follows from part E, right? Every point in B can be joined to P by a length minimizing geodesic. Yes, is this clear? Yes? Are you there? Yes,
Yes.
can someone reply? Is this fine?
Yes, it's fine.
Okay. Yeah, so please reply if I ask, because otherwise I don't know if you're listening or not. I mean, it's hard to say. So, I mean, feel free to reply. You can just unmute yourself and reply. There's no problem. Okay, so what does that mean? That means B is contained in the image of a closed and bounded set. The exponential is a continuous map. So X of this closed and bounded ball is compact. So B is a closed subset of a compact, and therefore B is compact. All right. Okay, so that's A implies B. And then B implies C. We have to show that if closed and bounded sets are compact, then M as a metric space is a complete metric space. So that's also easy. If you take a Cauchy sequence Pn in M, then any Cauchy sequence in a metric space is bounded. So Pn is contained in some closed and bounded ball, right? B closure. And since the closed and bounded ball is compact, Pn has a convergent subsequence. But if a Cauchy sequence has a convergent subsequence, then the whole sequence is convergent, right? This is true in any metric space. So therefore, the sequence Pn is convergent, right? So any Cauchy sequence is convergent. So M is complete. Is this clear?
Yes.
Okay.
Yes.
All right. Okay. And then we have C implies D. So C implies D says that if the metric space is complete, then the manifold is geodesically complete. Okay. So for this, we can just use totally normal neighborhoods. So I've written a proof here, but let me just draw you the picture and it will be obvious what I'm doing. So proof of Hoff-Reno. So C implies D. So you're given that MD complete. Let gamma from I to M be a unit speed geodesic. So geodesics, remember, correspond to integral curves of the geodesic vector field on the unit tangent bundle. So we know that for any smooth vector field on a manifold, for any initial condition, there is a unique maximal integral curve, right? That means an integral curve defined on an interval, which cannot be extended to any strictly larger interval, right? So therefore, we have maximal geodesics. What we want to show is that the maximal geodesics are defined for all time, right? So let gamma be a maximal unit speed geodesic. We want to show that it's defined for all time. Okay, so suppose not. So suppose that the interval is, let's say the supremum of the interval is finite. So let me call that, say, B equal to sup A, sup I, sorry, is strictly less than plus infinity. So then you let Tn be a sequence in I such that Tn increases monotonically to B. Okay. Then look at the points gamma Tn. So I'll just draw you the picture. So here is gamma Tn and gamma Tn. Okay. So because gamma is unit speed, the length of this segment is at most mod Tn minus Tm, right? So, so because gamma is unit speed, so the distance between these points is at most mod Tn minus Tm. So the distance between gamma Tn, gamma Tm, this is less than or equal to mod Tn minus Tm, and Tn's are converging to B. So this tends to 0 as Mn tend to infinity. So that implies that the sequence gamma Tn is Cauchy, right? And so therefore, by our hypothesis that the manifold is complete as a metric space, there exists a point P in M such that gamma Tn converges to P as n tends to infinity. So now all you do is very simple. You have the point P. So, okay, it's not on the geodesic maybe. So we have less than a minute. Let us stop here and we'll start again in the next session. So let's stop this meeting here.